Hey everyone, I'm Tommy Blunt, and this is Generating Macro Actions for Use in Planning and Reinforcement Learning. I'll be skipping over the background information surrounding reinforcement learning as provided by Stoll and Precup, as I'm assuming that the audience is familiar with the basics of these fields. We'll be taking a side-by-side analysis of two papers examining macro actions in the fields of planning and reinforcement learning. After going over the types of macro actions, we'll go over the steps involved for using these macro actions in each field. Analyzing problems, generating macro actions, filtering macro actions, utilizing them to solve problems, and finally, the results for using each type of macro action in both fields. From the planning perspective, the paper we'll be reviewing is Macro Fast Forward, Improving AI Planning with Automatically Learned Macro Operators. This paper deals with macro actions as macro operators, also known as macros. It uses two different generation methods, one being component abstraction, enhanced domain, where an original strips domain is enhanced to add support for macro actions, and solution enhanced planner, where the actual planner is enhanced to add support for a separate type of action as the macro actions. It uses deterministic domains and generates short action sequences. This picture comes from the International Planning Competition, where this planner was used to win 3 of the categories. From the reinforcement learning perspective, we'll go over learning options in reinforcement learning. This paper deals with options as the form of macro action, which operate in stochastic environments, making them stochastic themselves. They utilize domain-specific knowledge in the planning process and generate long sub-policies. The macro actions from the planning perspective are macro operators. These macro operators are simply a sequence of operators that are applied. They take a variable input, just like a regular operator, and have parameters, a preconditions, and some effects. However, the preconditions and effects are not explicitly specified for the extended planner variant and are instead generated from the actions inside of them. This will become important later as we take a look at the difference between these two variants. On the right, you'll see the generated macro action or macro operator, unload drop, that was taken by combining unload and drop. This is an example of one of the enhanced domain actions, as it's written in the exact same encoding as the other actions. You can see that the parameters, precondition, and effect are all calculated in this case. From the reinforcement learning side, we deal with options. Now, options are applicable in a set of initial starting state, and they follow a learned internal policy. The paper that we're going over by Stoll and Precup focus on deterministic policies, so policies that have one definitive action for every state. These options terminate with a probability based on the current state. So in this case, they use a target state where the termination probability for any other state is 0 and the termination probability at the target state is 1 to simplify the process. On the right, you'll see an example of an option with a target state right next to the hallway labeled T. You'll see that in general, the option tends to move towards this target state, and this was all automatically generated and learned as per the reinforcement learning policy. The planning paper offers two different approaches on how to generate these macro operators. One approach is component abstraction, which extends the domain. This is done by generating abstract components, as we'll go into later, and using these abstract components to follow generation rules and create macro operators that are inserted directly into the domain as actions. However, this makes it limited to strips models, as only the strips models are simple enough to compile these actions into one action written in the same way. For example, other subsets of PDDL, like ADL, have conditional effects which cannot be encoded by a simple macro operator written in the extended domain approach. This approach improves heuristic evaluation and reduces search depth. These are two important factors on making macro operators useful in planning. The other approach is the solution approach, which uses an enhanced planner. This is the approach they ended up using in the planning competition to win 3 of the categories. It extends the planner to support macros as additional input, instead of just using a regular strips planner and extending the domain. This allows it to extend across many subsets of PDDL, including ADL, meaning that you don't have to specify the preconditions and effects for these macro operators. It reduces search depth, but does not influence heuristic evaluation, as we'll get into a little bit later. The first step to generating macro actions is to analyze the domain. In the planning paper, this is done in the component abstraction enhanced domain approach by building a static graph. On the static graph, nodes are constant symbols such as strings or numbers, and edges are static facts, where static facts are instantiations of a domain predicate that aren't part of any add or delete list of any actions, but are part of the initial state. Basically, any predicate that cannot be changed by any action and is true at the initial state. For example, connected Tempe Phoenix. If Tempe and Phoenix are objects in the domain and they're connected, the fact connected Tempe Phoenix is a static fact as long as there's no bulldoze action that removes the many roads connecting them, because it's always true for any plan in this domain. It's immutable. For domains with hierarchical types, we first expanded the lowest level for predicate classification. This means taking predicates that take multiple types of a hierarchical nature and separating them into predicates that take the base types. And then finally, using this process to generate static graphs and combining them back into hierarchical types if possible. If all of the subtypes of one supertype have the same static graph, you can combine them. Otherwise, you'll have to keep them separate. This method of handling hierarchical types in their most concrete forms is necessary because in a domain with hierarchical types, instances of the same predicate can be both static and fluid. If there exists a predicate located at that takes a type locatable, the fact located at Tempe CAVC is static, while the fact that located at Tempe Tommy Blunt is fluent, as there exist actions that can change the location of me but not buildings, although both are locatable types. After generating the static graphs, we're able to build abstract components using a clustering procedure. First, we choose a seed type, a random type in the domain, and initialize components by creating one abstract component of each node of the seed type. Then we're able to extend components by adding connected nodes without merging subgraphs. This means that we can add edges to the subgraph as long as the edge does not share nodes in two different subgraphs, basically meaning that abstract components do not become merged. Then we apply limiting rules, which are specific to the planning process and help generate useful macro actions. One example of a limiting rule is limiting the number of low-level types within a component. For macro fast forward, the number of types is restricted from 2 to 4, with a goal of limiting the size and scope of macro operators. The diagram shows a static graph for the rovers problem, with the abstract components of type store, rover, camera circled. In this case, these were generated by choosing the seed type rover and generating a abstract component for those. Then the store and the camera were both connected, while the objective and the color and the points were not connected as they are shared by multiple components. Then we assign each abstract component an abstract type. The solution extended planner approach offers a different way of analyzing domains to generate these macro actions. First, we solve training problems with no macros in use to generate plan traces. Then we create solution graphs from these plan traces, where the nodes are actions from the plan and the edges are step interactions. These plan step interactions are defined for two actions if they're consecutive in a plan and either have at least one common argument or one of the actions has no arguments. This means that only two action sequences will be considered as macro operator candidates. This is done to generate cohesive macro operators. Actions that have no common arguments are often not relevant to each other and should not be combined in macro operator search. Here's an example of an excerpt of a Bloxworld plan trace that could be used to extract a solution graph. As unstack red blue and put down red both share a common argument and are adjacent in the plan trace, the solution graph for this plan trace would include an edge between these two actions. In the reinforcement learning paper, we analyze environments by first selecting a set of start states S and target states T. This is done with a uniform probability if we don't have any domain-specific knowledge, and if we do have domain-specific knowledge available, we use that to influence these choices. For each pair ST, or a start state and a target state, we perform a number of training episodes of Q-learning to learn a policy from S to T. Then we perform a number of test episodes using that learned policy and record the visitation count for each state to find the most visited states in several different types of start target state pairs. This method of analysis is similar to that of the extended planner example in the planning paper, as both extract domain information by solving extra problems and analyzing those solutions. Otherwise, the planning agents and reinforcement learning agent all perform different procedures when analyzing their problem domains for macro action selection. While the reinforcement learning agent records the visitation count for each state to find high traffic states that could be useful for future problems, the extended planner instead records common interacting action pairs in order to directly suggest those as candidates for macro actions. After analyzing the domain, the next step in using macro actions is to generate macro action candidates. Now I'm calling these macro action candidates instead of just macro actions because after this step, these candidates are filtered out into the useful set of macro actions. First, we generate an empty macro for each abstract type AT. Then, new operators are added to this macro. The space of operators starts out with one operator for every primitive action given in the initial domain description. The preconditions of an operator are added if they're not already in the add list of the macro. The delete effects are added if they're and are removed from the add list of the existing macro, and add effects are added and removed from the delete list of the existing macro. This has the effect of adding the new operator to the end of the existing macro operator, creating a combined action that has the effects and preconditions of both. The new actions to be added to a macro operator are added from a selective search in the space of operators using the following filtering rules. The negated precondition rule means that the operators with the precondition in the current delete list are pruned. These actions cannot take effect after the macro operator, as their preconditions will certainly not be met. The repetition rule means that the effects of the first K1 operators cannot be the same as the first K2 operators if K1 is less than K2. This means that if operators between K1 and K2 have no net effect, those operators have no use and should be excluded. The chaining rule means that for consecutive operators O1 and O2 in a macro, the preconditions of O2 must include at least one positive effect of O1. This is motivated by the idea that a macro should have a coherent meaning and not try to do two unrelated things at once. Macros are also size limited by length and number of preconditions. This is to reduce the preprocessing costs and prevent blowup of cost per node. Finally, the locality rule. This rule is meant to prune macros that change two or more abstract components at the same time. Firstly, the local static preconditions of macro M with abstract type AT are the static predicates that are both part of the macro's preconditions and the abstract type's edges, which are the predicates defining each abstract type. The locality rule states that the graph of these local static preconditions should be a subgraph of the abstract type itself, ensuring that only one component is changed inside the macro. In the extended planner approach, the macro action candidates are generated by extracting them from the solution subgraphs. The arguments from the solution subgraphs are replaced with generic variables. This is done by assigning constant symbols variables to preserve the variable mapping between the arguments of the containment actions. These use the same generation conditions as the extended domain approach, except there's no limitation on precondition count, as the number of preconditions is not critical for macros in this type of planner. No locality rule, as the locality rule relied on the concept of abstract components and abstract types, which are not needed for the extended planner approach, and a modified chaining rule, which replaces the precondition check with the same check used to mark action interactions in the analysis step. In generating option candidates in reinforcement learning, we focus on the most visited states. We choose the most visited state, Tmax, by finding the state with the highest visitation count as calculated during analysis. Then we calculate NS Tmax, the number of times each state S occurs on paths that go through Tmax. Then we compute the average number of times a state appears on paths that go through Tmax as a useful baseline. Then we set the initiation state to be the set of states that appeared on the paths that go through Tmax more than average, suggesting Tmax is more reachable from these states, given the option a good chance of succeeding. Using domain-specific knowledge, it may be possible to further refine the initiation set through interpolation. For example, in a grid environment, as given in the paper, taking all states within the bounds of the smallest rectangle that contains all states selected by the initiation set as the new initiation set would be a good method of interpolation. Without this interpolation, this agent still functions, although the extent to which it does is not covered by the paper. Then, finally, we reduce the state visitation count for each state by the number of times the state was visited on paths that went through Tmax, NS Tmax. This reduces the chance that several options will cluster around the same states, providing more useful options that can be applied to a variety of different goals. The option's internal policy is learned using standard Q-learning, and where the only reward is granted by reaching the terminal state Tmax. Since the planning agents work with parameterized actions and state variables and are able to analyze how action pairs affect those variables through their domain descriptions, actions can be combined in meaningful ways to accomplish general tasks that are useful for planning. However, reinforcement learning agents have much more limited information about their environments. And since states are generally atomic, the value of an action sequence heavily depends on the current state, making them less useful. This is why options are a more effective macro action approach than action sequences for reinforcement learning agents, as being able to reach a useful state is more beneficial than executing a predetermined sequence of actions for any arbitrary state, especially for stochastic actions. After macro actions are generated, they're filtered in order to select only the most useful ones. To reduce pre-processing cost, the simplest problems in this domain are used for gathering macro usage rates. For each plan, every macro used gets a flat 10 bonus points, plus 1 point for every occurrence in the plan. The value of 10 here was not specifically tuned using any method, but seems to provide balanced results. This prioritizes actions that are used often and many times within a plan, indicating that they might be useful in future planning. While this method is simple and fast, it does not take into consideration factors like node expansion count, problem difficulty, or macro succession application. This is one of the main motivating factors for using the extended planner approach, as shown in the next slide. To rank macros with the extended planner approach, they're all first assigned an initial weight of 0, with lower being better. Then, for every macro m extracted from training problem P, we calculate L, N, and N sub m by resolving P with and without m. L is the length of the solution when no macros are used, and N sub m are the number of nodes expanded to solve the problem without and with P respectively. Using these, the usefulness factor, delta m, is calculated by applying the sigmoid function, as shown below, to the quotient of the number of nodes saved by using m over the number of nodes expanded without m. Then, we update the weight for each macro by subtracting the learning rate times the usefulness factor times the length of the solution without macros. L is used to provide a difficulty factor, weighting macros that solve difficult problems more than those that solve basic problems. To filter these macros based on their ratings, a weight threshold W imaginary macro is calculated as an upper bound. This threshold represents the weight of an imaginary macro with a constant, small positive effect. Starting at 0, this imaginary weight is updated for each training problem in the same way as the macro weights, except substituting a constant c inside of the usefulness factor calculation. In the paper, c was set the arbitrary small constant of 0.01. While the use of arbitrarily defined constants is most prominent in reinforcement learning with learning rates, discount factors, and exploration factors, the process of filtering these abstract actions brings some of that into the world of planning as well. Just as reinforcement learning has to make decisions about risking the exploration of dead nodes or getting stuck at a local maxima, both fields are attempting to solve an optimization problem given limited information in consistent ways. These constants, whether their purpose be to guide learning and exploration or cull ineffective macro operators for planning, both serve to guide these agents to do the best they can in a variety of environments. As for the options approach in reinforcement learning, filtering is very simple. As option candidates are generated in order of most visited state, no further filtering is necessary. The generation process is repeated until the desired number of options is reached, leading to a small set of good options. Finally, after generating and filtering, these macro actions are utilized in planning and reinforcement learning. In the enhanced domain approach of the planning paper, the problem domain is enhanced by encoding the chosen macros as additional actions in the problem domain. These actions have preconditions and effects that are calculated using macro generation, and then a normal strips planner is used to make the plans in this enhanced domain. As shown before, this action on the right is a generated macro operator action that combines the actions unload and drop. In the enhanced planner, macros are utilized by extending a normal PDDL planner. In this paper, they used the fast forward planner with the ability to handle macro operators. This is done by adding the successor states for macros to the search space of the planner, ordered before the regular successors of a state. However, the benefit of putting these successor states directly in the search space can be canceled out by the large increase in branching factor if all macros are considered in every state. To prevent this, a helpful macro pruning heuristic method is used. A relaxed problem is solved where actions have no delete effects, and only macros where each action of the macro is an action of this relaxed plan are considered. This is similar to the concept of the initiation set in reinforcement learning options, where macro actions are only considered for a subset of the state space. However, in planning, these compatible states are not calculated ahead of time as they are in the generation of options. To utilize macro actions in reinforcement learning, the action value function Q is extended to support options. The value for taking option O in state S given policy mu is the expected value of the discounted rewards given by following the option until it terminates and then by following mu. Then either semi-MDP Q-learning or intra-option Q-learning can be used to learn a policy over a set of options. This set of options includes both the primitive actions as trivial options as well as the generated options. For semi-MDP Q-learning, Q is updated after an option is finished executing using this equation, where state S is the state the option was initiated in, S prime is the state the option terminated in, R is the cumulative discounted reward from executing the option, and K is the number of steps between S and S prime. This has an unfortunate downside that option values are only updated after an option terminates, so they're hard to use in cases where options take a long time to execute. Another approach is intra-option Q-learning, which is a method of temporal difference learning that uses options. In this case, Q is updated at each time step using this equation, where beta is the termination probability for option O at state S. This allows Q to be updated for every time step, extracting more training information from the same amount of experience and for allowing learning from options that are never fully executed. That leaves us with the results. So how did these macro actions perform in a planning problems? The authors entered a version of the fast-forward planner called macro fast-forward into a planning competition, using their extended planner approach to macro operators. These graphs show the performance of the extended planner approach on 3 selected test domains: satellite, optical telegraph, and dining philosophers. In these domains, the macro fast-forward planner outperformed the normal fast-forward planner by a sizable margin, which allowed the macro fast-forward problem to win these domains in their planning competition. However, the macro-enhanced planner did not outperform the base planner in every domain. In the domains of Pipes World and PSR, performance of the macro-enhanced planner was much closer to that of the base planner. In Pipes World, no tankish, non-temporal. While macros did lead to a significant speedup, allowing the planner to solve 4 extra problems, it failed to solve 3 problems that were solved by the base planner. The tankage version of this domain had a less significant difference in performance between the 2 planners. Finally, in PSR, macros led to little or no impact. This seems related to the overall complexity of each domain. The table shows the training problems and total training time in seconds for each domain. In the domains that macro fast-forward was most successful in, it was able to generate useful macro operators in a relatively short period of time. However, for other domains, the planner took much longer to train, showing that useful macro operators were much harder to find. But what about how the enhanced domain approach compares? This graph shows the performance of using neither approach, each approach separately, or both approaches combined. Interestingly, the authors found that combining both approaches often leads to better performance than using them separately. In rovers, the combined approach performs the best, while the enhanced domain approach offers better results in depots. In the domain depicted by these graphs, satellites, the enhanced domain approach along with the combined approach suffer, failing to solve 3 problems. This is related to the cost per node in the searches of either method. In the satellite domain, the cost per node increase from using the enhanced domain approach is prohibitively expensive, leading to some problems not being solved in time. Overall, while computation time varied between macro fast-forward and normal fast-forward planners, there was no significant impact in macros on solution quality, measured as plan length. So how did the reinforcement learning macro actions compare to the planning macro actions? Well, in reinforcement learning, generated options offered similarly mixed results. The domain used for testing was a simple grid world domain with stochastic movement, moving in the expected direction with probability 0.9, or moving to one of the 2 sides with probabilities 0.5 each. The domain was set up as shown in the diagram, with 4 rooms with hallways connecting them. For these tests, 30 runs of the option generation algorithm were run, each generating 8 options. An example of the generated option is shown by the arrows marked on the image. Squares without arrows were not chosen as start states or visited at all during the intra-option Q-learning. The algorithm chose a target state close to a hallway, and actions that navigate towards that state seem to be mostly preferred by the generated policy. These graphs show the performance during training and testing for reinforcement learning agents using either only primitive actions or one of either option learning methods. Each agent was trained for 150 episodes with a given goal location, and then the goal location was switched out without resetting the Q values, simulating a situation where the agent is not explicitly told the task has changed, but has to learn how through trial and error. In this domain, it seems like the options perform better at the beginning, but then fall behind when compared to primitive action-based reinforcement learning. Even when the goal is changed, when the authors predicted it would cause the option-based learner to perform significantly better than the base learner, the situation remained the same. The main reason for this is these generated options only terminate in the target state and are unable to terminate early in the case that the option takes the agent further from the goal. This means that higher weighted actions and options may have different consequences, as actions may only set you one state away, but choosing an option that is not good for the current state will give you a state that's very far away. Interestingly, in a different domain, the blank grid world, the options approach performed much better, for there's no obvious hotspots that can be used to navigate to. As shown in the diagram and graph, options were still able to be generated in this domain, and utilizing them in learning led to greater robustness to goal changing, just as the authors predicted, as the option-enhanced learner was able to more quickly adapt to the new goal state. Just like some domains proved more conducive for macro action planning in the planning world, some domains seem to work better with options and reinforcement learning. These are the references for the 2 papers I discussed in this slideshow. Thank you so much for taking your time to watch my presentation, and please let me know what you think in the reviews.